Hi, this is group Should Have Done compsci, and this is our presentation for ENSC 450 final project. This is Andrew Chen speaking, and my partners are Jordan and Puru. This will be the outline for our presentation. First, we'll go over the objective and purpose of our final project. Then we'll be talking about some background information. Next, we'll be talking about how we amended our core for SOC integration, as well as how the SOC works and test bench scenarios. Next, we'll be talking about creating a hard macro for our core, as well as design specs for our front end and back end and performance results. And then we'll talk about hard macro integration with SOC front end and back end, and the SOC performance results for front end and back end. Next, we'll compare hard macros versus our SOC design results, and we'll go over a conclusion in the end.
So for some background, our core that we chose was the AES 128 key. And what that is a advanced encryption standard method. So basically it takes two inputs. One is a 128-bit plain text and 128-bit key. And it will encrypt the plain text using the key, and it will produce an encrypted 128-bit output. So our goal is to integrate our core onto an SoC. So the motivation for making an SoC is that SoCs contain all the required circuitry on one chip with other components required to perform functions. So the advantage of this is that they're tightly integrated, meaning that there's improved performance and lower power consumption due to the small size that we create these on. And this is better compared to multi-chip designs with the same functionality.
The objective of this final project is to take what we have been learning throughout the semester to fully incorporate our chosen core into a given system and perform PNR. To do so, we first have to adjust our core so that it fits into our system on chip. Then, we'll build a hard macro for our amended core, which we can then use in the front and back end procedure and verification. Then, we integrate our macro into the system on chip, and finally perform a PNR on our full system on chip system.
So for some background, our core that we chose was the AES 128 key. And what that is a advanced encryption standard method. So basically it takes two inputs. One is a 128-bit plain text and 128-bit key. And it will encrypt the plain text using the key, and it will produce an encrypted 128-bit output. So our goal is to integrate our core onto an SoC. So the motivation for making an SoC is that SoCs contain all the required circuitry on one chip with other components required to perform functions. So the advantage of this is that they're tightly integrated, meaning that there's improved performance and lower power consumption due to the small size that we create these on. And this is better compared to multi-chip designs with the same functionality. So in order to amend our core for SoC integration, we first noticed that our core has an I/O of 128 bits, while our bus has a I/O of 32 bits. And so we needed a way to interface these two. And so our solution was to create a buffer which would act as a wrapper for our core. And so any inputs and outputs would have to go through our buffer first. So what our buffer basically does is breaks up our 128 bits into 4 chunks, and so that it can interface properly with our 32-bit bus. And so you can see our inputs take 4 clock cycles each. And since we have 2 inputs, it will take a total of 8 clock cycles for both plain and key. And our output takes 4 clock cycles. So we also created counters, and this was so that we could understand when it finished reading or writing one of our inputs. And we also used MR and MW control signals. And this would let us know basically if the master wants to read or the master wants to write. And we would handle these cases appropriately. And we also created different addresses we assigned for each plain, key, and cipher to know which to read or write from. So here's an overview of how our SoC system works. So we are dealing with different components here in our SoC, which include our CPU, SRAM, DMA, our core, and a bus. And so you can see in the picture on the right, this is just a really high-level block diagram. So basically, we have all our components here: our CPU, SRAM. Forgot to mention counter. We have a counter as well. DMA, our buffer that we implemented, and our core. And so all these components, they communicate using this 32-bit memory bus, and that is how the masters and the slaves communicate with each other. So in this case, the CPU will be the master. DMA is also basically an embedded master and slave, and everything else here is a slave. So SRAM is a slave, and our buffer is a slave. And so for example, if the CPU wants to communicate with our core, it'd have to send a signal through the memory bus, and our buffer would receive that control signal. And so basically what we have here is just master-slave interaction using 32 bits. And so our main function of this SoC is basically just our AES core, but it is possible to add more cores to our SoC, which would add more functionality. The CPU. So in our SoC, we have a CPU, and this acts as a master component. The CPU will generate instructions that it wishes to fulfill. So during development, our test bench will act as a CPU. So for example, we'll have memory read and memory write instructions that the CPU wishes to complete, and it'll specify which component or which slave that it wishes to talk to via addresses. And so, for example, it might say, oh, I wish to read from the SRAM. And so it'll specify MR as the control signal, and it'll specify the SRAM's base address here, and that's how the master can communicate with SRAM. And so instructions are carried out by the different components of the SoC. And so some possible CPU actions in our SoC include reading and writing to SRAM, reading and writing to core, initiating data transfers via the DMA, and communicating with basically any slave component using the bus. So another component that we have is the SRAM. So the SRAM is a slave component. It's basically a memory component that enables us to store any intermediary data. So it'll allow the masters and slaves to read and write to and from SRAM. And in addition, it can also allow the direct memory access from an SRAM to our core, for an example. So this is already given to us as a hard macro.
The DMA is an embedded master and slave component in our SoC design. The DMA is what facilitates data transfers between master and slave components without the need for CPU to take action. For example, the CPU can tell the DMA that it wants the cipher output from our core. And so then the DMA, what it will do is tell the core to read the data from SRAM, calculate that, and then write the data back to the SRAM, and the CPU can then take that data. The counter. The counter is a slave component, and it is designed to estimate performance. It counts the clock cycles taken to perform an action, and there can be many different counters going off at a single time. So what the CPU can do is issue a command to counter number 4 to start counting the clock cycles for a given process. And later on, when the CPU wants to retrieve the data, it can issue another command to counter number 4, which tells the counter to stop counting, and then at that point the CPU can read the count.
So in order to test that we amended our core properly, we needed a test bench to test that our core can interact with the other components of our SoC. And so in our test bench, we test for 3 main scenarios: reading and writing data straight from our CPU to core, core reading and writing to SRAM via the CPU, and using the DMA to facilitate transfers to and from the SRAM and core. And so in the next clip, you'll see us demonstrate us going through our test bench and viewing the waveforms to ensure that our test bench scenarios are met.
So this is the test bench, which is going to be used as a CPU of our SoC. In the beginning, we have a counter that will be used to time all of the example test cases. This is counter number 0. Then we have 16 write commands to the SRAM, where in the first 8 32-bit packets, we're writing the plain text and the key that's going to be used as inputs to our AES encryption core. The first 4 packets are going to be the plain text. The next 4 are going to be the key. Then we write 8 more packets of just filler data to the SRAM. So here comes our first test case. In this one, the CPU is going to be sending data and reading from the AES core directly. And so the AES core is being interfaced through the AES buffer. We can see that the CPU writes the plain text and then the key. The addressing is just linear. 1 2 3 4 writing to address 1 2 3 4 1 to 4 will be the whole of plain text, all the 128 bits of the plain text. Writing to address 5 to 8 will represent all 128 bits of the key, and then reading from 9 to C will represent the bits of the output, which is the cipher that the AES core outputs. And then we read the value of the counter for this specific that's going to be used to time this specific test case from counter 1. Now comes the second example. In this one, the AES, the CPU is going to read from the SRAM the data we wrote before, and then it's going to input that into the buffer and read the outputs. And we're also timing that with another counter number 2. Then there's the third example, third test case, where the DMA is going to read, where the SRAM is going, where the AES core is going to talk to the SRAM through the DMA. So the DMA is going to read data from the SRAM and then write it to the AES core as inputs. And just so that there's some variation in the data, we're modifying, before we start this test, we're modifying with these 2 commands what data will be written to the AES core. We're modifying the SRAM data. Now let's look at the waveforms. So here we see the first test case where the CPU is writing directly to the AES core. The CPU sends a write command for the first packet of the plain text, and the AES core receives it and increments the plain counter. And when it receives all 4 packets of the plain text, the plain counter is now all ones. And same thing with when the CPU writes all 128 bits of the key to the AES core, then the key counter is all ones. And when that is the case, the AES core starts computing, and it keeps computing, and then eventually after about 600 nanoseconds, the answer is ready. The cipher is ready to be read. Then here the CPU reads the cipher, and we can see these 4 because the output is 128 bits, so again it's read in packets of 32 bits, and as we can see, they are the same data that the AES core output. Now, here we're reading the counter value for how long the first test case took, and it took these many clock cycles. And then the second test case comes. Here we reset and start a second counter for the second test case, where the CPU is reading from the SRAM and then writing that to the AES core. Here we see this data is being read from the SRAM and then being written to the AES buffer. And same thing again, this happens in 4 chunks, and the plain text is fully received by the AES core, and the counter is all ones now for the plain text. And since the cipher text is all zeros in the SRAM, you can see it's all zeros, but it still gets received, and the counter for the key, the counter for the key becomes all ones, and counts up to 16, and then it's ready, and the AES core starts computing, and it computes for about 600 nanoseconds again, and the output is ready to be read now. By the way, we have checked using third-party tools if given these values as the key and the plain to the AES algorithm, what's the output, and these outputs match that. So we know that the AES core works and is implemented correctly on this SoC. Now the CPU reads these values in 4 packets. This output value of the ciphertext, it reads it in 4 packets and writes it back to the SRAM. And that took the second test case took these many clock cycles. Now starts the third test case, where the DMA is being told to read. Before that, we're modifying the data in the SRAM just so that there's some variation. The DMA is being told to start reading from this address in the SRAM and start writing to this address at the AES core. And for both, the step size is 1, and the DMA will perform 8 such transfers, thus effectively transferring the 4 packets of the plain text and the 4 packets of the key. And those transfers are taking place here, as we can see. The plain text counter of the AES core buffer is counting up all the way. It reaches the value 16 when we know all the bits of the plain text have been received. And the same thing happens for the key input bits. And when both the inputs have been received, then the AES core starts computing again, and it computes, and produces an output, and this output is then again read by the DMA and written to the SRAM, and we can see that here. And just for a quick overview of so that we can see that the AES core is properly integrated into the SoC. Here in the first test case, these are the values, and this the input values to the AES, and this is the output. And we designed the test cases so that even though the data is being inputted to the AES core from different sources, it's the same data, and as we can see, given the same data, it produces the same output. So this verifies that the AES core has been properly integrated into the SoC. And this test bench, our AES integration passes this test bench for both the front end and the back end.
To create a hard macro of our core, we ran the full PNR procedure. We confirmed afterwards that there were no timing DRC and slack violations. We made sure that there are also no hold time, setup time, or max tran violations. And so after this step, we obtained the .def, .lib, and .left files, and these are useful for our hierarchical design later on when we integrate our macro into our final SoC. So here you can see our front-end and back-end results of our hard macro of our core. So if you'd like, you can pause here and take a look at our results.
When designing our SoC, we began by placing down instances of our hard macro. We placed our core and SRAM instance in a way that the pins would have room for wires to extend outwards. Since the left side of both instances have no pins, we moved them as far left as possible. There were a few other things to consider as well when designing our SoC. We wanted a chip area to be as small as possible, and we also wanted to achieve a target frequency close to that of the front-end results. To do so, we first set the frequency to be the same as the front end, and then began shrinking the chip size. We would keep shrinking the size until we reached a reasonable slack and made sure there were no violations.
And here's our SoC after the final backend synthesis, place and route. Since we had to use the AES core and the SRAM as hard macros, and they both are pretty square, we thought it best to manually define the dimensions of the chip to be rectangular. So as we can see here, the SRAM and the AES core are both implemented as hard macros. And after the place and route, we get no timing violations and no DRC design rule violations. We have a slack of 1.392, and our target clock time period is not 11 nanoseconds. So we're running at a clock of 11 nanoseconds. This is our critical path. And so the slack for our critical path is 1.39. And yeah, now let's look at it without the power stripes. So removing metal 6 and metal 7. This is basically our placed and routed core, and we feel that we achieved a pretty good density with our final design.
So here you can just see our SoC performance results for the front end and back end, and feel free to pause if you'd like to take a look at the results here. So to conclude our presentation, by integrating our core into an SoC, we are able to save power, space, and improve performance, versus if the components were fabricated individually. The benefit of SoCs include being more efficient, as the components are generally packed close together and reduce timing delays. So overall, this project has allowed us to understand the purpose of hard macros and how they can be used in hierarchical design. And in addition, how SoCs can also apply the concept of hierarchical design to achieve even greater designs that include possibly multiple cores and other components that make up a system on a chip. So in this lab, we created a very simple SoC, but we understand that we can create a much more complicated SoC by adding things such as additional cores and additional system-on-chip components. But nonetheless, during this lab, we learned a lot about what hard macros are, what SoCs are, and how we can prepare them for fabrication. Thank you for listening to our presentation.